Welcome to The Explainer. So today we're diving into a topic that is honestly incredibly relevant to pretty much anyone writing code right now. We're talking about the relatable, sometimes magical, and yeah, often deeply frustrating reality of using AI coding assistants to refactor your projects. Like if you've ever blindly accepted an AI suggestion only to spend the next 3 hours untangling a massive mess, yeah, this is exactly for you. We're looking at a specific case study today that just perfectly highlights how easily things can go completely sideways when human intent meets artificial intelligence. Now, you might be wondering, can a so-called smart AI code suggestion actually make your code worse? I mean, we kind of just naturally assume that because an AI can parse millions of lines of code in a fraction of a second, its structural recommendations must be fundamentally sound, right? Well, we are going to explore this exact question by following one Haskell developer's recent experience. As you'll see, we're going to track how a seemingly brilliant, completely logical AI suggestion totally morphed into an unexpected trap that just derailed an entire refactoring session. Section 1. The AI Code Suggestion. Okay, so our source material today comes from a developer journal by an author named Ang. And Ang essentially asked an AI model to help refactor a custom type called app error. The AI looked at the codebase and basically said, hey, right now you're taking all these different errors and just flattening them down into generic strings. And if you're a developer, you already know that relying on generic strings for error handling is, well, it's a bit of a mess. It's hard to parse, and it's super prone to typos. So the AI suggested an alternative. Instead of generic strings, let's upgrade to preserving structured, type-safe error data. By keeping the underlying errors totally intact within the app error type, the application becomes just way more robust and predictable. Conceptually, this is a massive upgrade. It's exactly the kind of smart advice you'd expect from a senior engineer. Section 2. Refactoring the app error type. Naturally, Ang was pretty excited by this cleaner architecture, accepted the premise, and started the process. But real quick, before we see what happens next, we need to touch on two absolutely foundational concepts in Haskell, EQ and show. Now, let's not get bogged down in dense category theory here. Basically, EQ simply provides the rules for equality. It tells the compiler how to check if two things are identical. Show provides the rules for display. It tells the compiler how to turn a piece of data into a string so it can actually be printed to the screen, like in an error log. In Haskell, if you want to compare two custom errors or print them out for a user, your error type absolutely must implement these two rule sets. With those basics out of the way, let's look at the AI's proposed roadmap for this refactor. Step 1, we update the type signature for our app error. Step 2, we update the constructors to preserve that beautiful structured error data instead of the old strings. And step 3, this is the magic step. We use Haskell's built-in capability to automatically derive eq and show. See, Haskell has this amazing feature where, instead of manually writing out all the rules for equality and display, you just type deriving eq show at the end of your data declaration, and boom, the compiler writes all that tedious boilerplate code for you. It's elegant, it's fast, and it completely lulls you into this wonderful false sense of security regarding how smoothly this AI's plan is going to go. Section 3, the manual EQ trap. But here's where we get the abrupt record scratch. Up until this exact point, the AI looks like an absolute genius. But as Ang actually tries to compile this seemingly perfect code, the entire elegant process just completely derails. The crucial problem is this: the AI totally hallucinated the compiler's capabilities. Remember how we said the AI wanted to preserve the underlying error structures? Well, two of those underlying errors are io-comp error and pandoc error, and neither of those natively implement the eq rule set. Because those nested components literally do not know how to check themselves for equality, the parent app error type suddenly cannot be automatically derived. The compiler just throws its hands up in the air. That beautiful, elegant little line of code, deriving eq show, completely breaks down. The shortcut just vanishes into thin air. And this perfectly illustrates the nightmare that followed. Because the compiler can no longer generate those equality rules automatically, the developer is now forced to write a massive, tedious block of code totally by hand. Ang literally had to physically write an instance of eq for app error, going line by painstaking line, defining exactly how to compare file not found, not text file, invalid UTF-8, and so on. For the underlying types that couldn't be compared, like pandoc runtime error, Ang was forced to just write a blanket rule that basically says, hey, if they are both this type of error, just consider them equal and let's move on. The developer had to write all of this tedious manual matching just to make the AI's clean architectural idea function at all. When Ang finally stepped back and looked at this massive wall of manual equality checks, the reality of the situation really set in. Eng realized this specific part was, quote, a code smell that adds unnecessary complexity and completely undermines the benefits of the refactoring. Now, a code smell is just a term developers use for code that doesn't feel quite right, you know? It usually indicates a deeper problem in the design. The initial theory from the AI was super clean and type-safe, but the actual reality was a messy, bloated file full of manual mapping that completely defeated the purpose of a quick, elegant refactor. The smart suggestion actually ruined the simplicity of the code.
Section 4. Lessons in AI Refactoring.
You know, it's so easy to just get mad at the AI and close the window, but stepping back reveals pretty profound realization about our tools and what actually went wrong here. As Eng notes, either you subscribe to frontier AI models, or you must steer the model to suggest the simplest, most direct solutions. This gets right to the heart of the current state of developer tooling. If you're using standard, freely available AI models, which might have slightly older or maybe less rigorous training data regarding strict languages like Haskell, you just cannot blindly accept complex structural changes. You, as the human developer, must be the pilot. You have to actively guide and constrain your AI tools towards simplicity, rather than letting them build these theoretical castles in the sky that just immediately collapse the second they hit your compiler.
So let's quickly summarize our key learning points from Eng's experience. First, high-level AI logic can easily fail when it hits strict language constraints. The AI knew structured data was better than strings, but it totally missed the exact limitations of pandoc error type classes. Second, complexity entirely undermines refactoring benefits. If an AI saves you 10 lines of code in one file, but forces you to write 30 lines of tedious boilerplate in another, well, you haven't actually improved your codebase, have you? Third, always evaluate the hidden costs of an AI suggestion before you start typing. And finally, and I think this is my favorite takeaway, failed refactors are still incredible learning opportunities. Eng noted that nothing was truly lost here. Figuring out why the AI was wrong forced a deeper understanding of Haskell's type system, which is honestly the entire point of the journey.
Which brings us to the end of our explainer today. And I want to leave you with this provocative question to chew on. How do you audit your own AI coding assistance? When an AI drops a suggestion that looks incredibly smart, do you have a system in place to verify the hidden boilerplate it might be dragging in behind it? Are you steering your AI, or is it steering you right into a manual coding trap? Think about that the next time you're tempted to hit accept on a massive code block. Thank you so much for joining me to explore this fascinating breakdown. Keep building, keep learning, and as always, stay curious.